Hello children, your Vanashri ma'am is back with another lesson in physics, namely radioactivity. Now this lesson, radioactivity, is your last chapter in your textbook. This is chapter number, wait, let me tell you. This is your chapter number 12, okay, radioactivity. This has definitely a weightage of 4 to 6 marks in section B. But still the weightage keeps changing. The council does not stick to any one particular weightage. So let us learn. This is a very small chapter, more of theory. Okay. So let us complete this. Now, before I go actually explaining to you what is radioactivity, let me brush up your previous knowledge because that will be very useful to you in understanding radioactivity. So, you already know, children, you are aware of the definition of atomic number, right? You remember this? Atomic number. This is denoted by capital Z. Okay. What is atomic number? Atomic number of an atom is equal to the number of protons in its nucleus, or which is same as the number of electrons in the atom outside the nucleus. Right. So atomic number denoted by Z, it is the atomic number is the number of protons in the nucleus, or it is same as the number of electrons present in the atom outside the nucleus. Okay, so atomic number Z. Then mass number. Mass number is denoted by capital A. Now what is mass number? The mass number of an atom is equal to total number of nucleons, that is total number of protons and neutrons present in the nucleus, right? They are together called nucleons, isn't it? Protons and neutrons are present in the nucleus of the atom, that is why they are together called nucleons. So mass number A is equal to the number of protons plus number of neutrons. Where are these two present? Present in the nucleus. So protons and neutrons are present in the nucleus of an atom, and together they are known as nucleons. Protons and neutrons together are known as nucleons. Okay. So What are the symbols that we use for these subatomic particles? Electron is represented by E and proton E minus. Proton is represented as P plus and neutron is represented as N0 because charge on it is 0. Okay, then the mass is represented as a subscript. Electron has negligible mass, proton has 1 unit mass, neutron also has unit mass. Okay, now the atomic model you have recently done in chemistry also, in 9th standard also you have done the atomic model. You have done little bit of atomic model in the chemistry in the chapter chemical bonding. Anyway, let us just brush up quickly the atomic model. Now the atomic model, you know, the nucleus is in the center of the atom, and say let me take the example of helium atom. Okay, so helium atom, okay, this is the helium atom. You can say it has 2 protons in the nucleus, 2 neutrons which are together called nucleons. Okay, 2 neutrons, 2 protons and 2 electrons. These are the 2 electrons, this one and this one outside the nucleus. You can say this is the nucleus, okay, of helium atom, which contains 2 protons and 2 neutrons. These are the neutrons and these are the protons, okay, and these are the neutrons. So the subscript tells us the number of protons or electrons and the superscript tells us the mass number. Okay, this is the generalized way of expressing. Okay, so helium 2,4 means the subscript 2 tells the number of protons or electrons, and this tells us the number of neutrons and protons, that is the superscript 4. It tells the number of neutrons and protons. Okay, is that clear? Now we'll discuss about a term which you have learnt in your smaller classes. Recently we haven't revised it or brushed it up. You must be aware of this term, so let me revise it. Okay, the term isotopes. Do you remember? Any bells are ringing? You have heard this term, isn't it? Isotopes. Okay, even if you don't remember, pay attention now. Isotopes are atoms of the same element having same atomic number but different mass number. Let me repeat. Isotopes are atoms of same element, but they have atoms of same element means they must have same atomic number, because atoms of same element means they will have the same chemical properties. So the number of electrons in the outermost shell are responsible for the chemical properties of a atom. So therefore, since isotopes are atoms of the same element, they all will have the number of electrons. Immediately it means they will have the same number of protons. So what do they differ in? They differ in number of neutrons. Now this number of neutrons, difference in number of neutrons, brings about minor changes in their physical properties. They don't affect the chemical properties. So all isotopes have same chemical properties, but they have slightly different physical properties. Okay, so let me define properly. Isotopes are the atoms of the same element, isotopes of the same element, having same atomic number. We denote atomic number by which letter? Z, but different mass number, we denote it by A. So atoms of same element having same atomic number but different mass number are called isotopes. Okay, so isotopes only differ in their physical properties. Okay, so atoms of isotopes have same number of protons, so implies same number of electrons but differ only on the number of neutrons. Since the isotopes have same number of electrons outside the nucleus, so their chemical properties are same. Okay, so the isotopes or atoms of isotopes, the the atoms of isotopes have the same number of protons and electrons. Now what do they differ? The atoms of isotopes have or differ in the number of neutrons. Okay, the atoms of isotopes differ only in the number of neutrons. Okay, so as the atoms of isotopes have same number of electrons, they have same chemical properties. But they slightly differ in their physical properties. Why? Because of the difference in the number of neutrons. Isotopes only differ in their physical properties. Okay, now I will show you. There are hydrogen has 3 isotopes, then carbon has 3 isotopes. Okay, chlorine has 2 isotopes. So one by one we will do the examples. Okay, examples of isotopes. Okay, these are isotopes of hydrogen. So what does this mean? See, isotopes, this hydrogen atom has one proton. This is the proton, okay, and this is the electron, okay. This is called deuterium. The name of this isotope of hydrogen is known as deuterium. Can you see? Deuterium. Let me make it little big. Okay. So this is one proton and this is one electron. Okay. This deuterium, an isotope of hydrogen, has one electron as usual, okay, but it has one neutron extra. There is no neutron in this. This is called protium. This is called deuterium, isotope of hydrogen. This has one neutron extra, okay, and this is the proton, okay. Now this is another isotope of hydrogen, tritium, which has one electron, one proton, it has two neutrons, So see, the isotopes differ in only the number of neutrons. The first, so these are all isotopes of hydrogen isotopes. So this one has no neutron, this one has one neutron, that is protium has no neutron, deuterium has one neutron, and tritium has two neutrons. So this is how the isotopes differ in the number of neutrons, but they do all of them have one electron in their atom, that is in their electron shells, revolving in the electron cells. All of them have one electron. So all of them are isotopes of hydrogen. They have same chemical properties, but they slightly differ in their physical properties because of the difference in the neutrons. Clear? Similarly, chlorine atom also has these isotopes. Chlorine has, carbon has. Okay. So now I'll show you isotopes of carbon. Now carbon also has three isotopes. Okay, so the atomic number of carbon is 6 and mass number is 12. So that means carbon atom has 6 electrons and 6 protons and 6 neutrons. That is why this has become 12. Now its isotopes have, the isotopes of carbon are this C612 is very much abundant in the nature. But the other isotopes are C613 and C614. So these two are not very abundant in nature, but they also exist. And these two, all the three isotopes of hydrogen, isotopes of carbon, have 6 electrons in their atom or 6 protons in their nucleus. Now This carbon atom has 6 protons and 6 neutrons, right? Because its mass number is 12. This isotope, 6 electrons, it is common in all. It has 6 protons. Since it has 6 electrons, it will have 6 protons, but it has 7 neutrons. Okay, so that is why its mass number is 13. And this isotope of carbon has 6 electrons, which is common, but in its nucleus it has 6 protons and 8 neutrons. Okay, so these are all isotopes of carbon, right? Then another example is isotope of chlorine. Chlorine has 2 isotopes. Okay, now chlorine atom, which is abundantly found in nature, is Cl1735. This implies number of electrons 17, number of protons also 17, and number of neutrons is 18. Okay, because its mass number is 18. So 35 minus 17. Okay, right? Now the other isotope of chlorine is Cl1737. That is Cl1737. This implies number of electrons 17s. Okay, 17. Then number of protons also 17. Okay, then number of neutrons 37 minus 17, so 20. Is that clear? So they differ only in the number of neutrons. The isotopes differ only in the number of neutrons. So I hope isotopes is clear to you. Yes. Now I'll give you one or two more examples. Tin. What is the chemical formula or symbol of tin? Sn. Do you remember? Sn. This has 10 isotopes, largest number of isotopes. Tin has largest number of isotopes. Okay. Now, some isotopes are stable and some isotopes are very not that stable or unstable. Now, the unstable isotopes actually lead to the radioactivity, lead to the phenomenon of radioactivity, or the unstable isotopes are the radioactive isotopes. Anyway, I'll discuss about them. First, let me go to radioactivity, then I will come back to this. Okay, but tin has 10 isotopes. Okay, then you have another element, uranium, which we will be learning in detail further in the chapter, which is a radioactive element. Uranium also has 2 isotopes. Okay, U92 235 and U92 238. Okay, uranium. U is the symbol. So U92 235 and U92 238. So usually the atoms of these heavy elements are responsible for the phenomenon of radioactivity. We will learn what it is radioactivity, then we will come back to these examples. Anyway, we will be dealing with this uranium in detail once I explain to you what is radioactivity. So till here isotopes are clear to you? Yes, my dear children. Then I will proceed to another definition called isobars. Okay. Now, what are these isobars? The isobars are atoms of different elements. Mind you, isotopes are atoms of same element, whereas isobars are atoms of different elements which have same mass number but different atomic number. Let me again explain to you. Isobars are atoms of different elements. They are not, isotopes are atoms of same element, but isobars are atoms of different elements. Isobars are atoms of different elements. Okay. Now what do they have similar? They have similar mass number, but their atomic number is different. So that means if atomic number is different, their chemical properties, their physical properties, everything are different. But what is common is their mass number. So atoms of different elements having the same mass number. What do we denote mass number with? A, capital A. But different atomic number. But different atomic number, that is Z, are called isobars. So isobars, they have different atomic numbers. So the number of electrons and number of protons, that is different, but the mass number, that is the total number of protons and neutrons, that sum is same. Okay. So the number of electrons outside the nucleus is always equal to number of protons. So number of electrons or number of protons, they are different in isobars. Okay. So total number of protons and neutrons is the same. Now examples. Examples of isobars. One is, say, sodium, its atomic number is 11 and mass number is 23, and magnesium, its atomic number is 12 but mass number is 23. These are isobars. Can you see? They have different atomic number but they have same mass number. Their mass numbers are same, but they are completely different elements. Sodium and magnesium have different properties, so they are isobars. Okay. Another example of isobars is carbon C614 and nitrogen 7 and 14 are isobars. C614 has 6 protons, 6 electrons, and the neutrons are 8, so its mass number is 14. And nitrogen has 7 electrons, 7 protons, and it has 7 neutrons, that is why its mass number is 14. So mass numbers are same. Isobars have same mass number but different atomic number. Okay, so these are examples of isobars. Okay, now if the number of protons and neutrons get interchanged inside the nucleus, then those two atoms are called mirror isobars. For example, mirror isobars. What are mirror isobars? If the number of protons and neutrons get interchanged in the nucleus of the atom, okay, then they are called mirror isobars. For example, sodium Na 11 and 23 and magnesium 12 and 23. Now in sodium inside the nucleus you have protons 11 and neutrons 12. In magnesium you have protons 12 and neutrons 11. Okay, can you see what is happening? The number of protons and neutrons are exchanged. Here number of neutrons is 12, number of protons is 12. Here number of protons is 11 and here number of neutrons is 11. So these are called mirror isobars, where in which mirror isobars are what? In which the number of protons and neutrons are interchanged. Okay, is it clear? Now we will learn another term called isotones. Okay, now what are these isotones? Isotones, atoms having different number of protons but same number of neutrons are called isotones. So they have different number of electrons. Now for example, first of all let me write down the definition. What are isotones? Isotones are atoms having different number of protons but same number of neutrons. Neutrons are same, protons are different. Protons are different implies electrons, number of electrons is also different. Are called isotones. Again example, Na 1123 and Mg 1224 are isotones. Why? Now in both of them, see what is there in sodium. See, number of electrons is 11, number of protons is 11, number of neutrons is 12. Now in this Mg 1224, number of electrons 12, number of protons 12, number of neutrons 12. See, so they have same number of neutrons. So therefore they are called isotones. Is that clear? Similarly, one more example of isotones is potassium, potassium 19 and 39, and calcium 20 and 40. These two are isotones. Are isotones. Okay? Why? Because K1939 has number of electrons 19, number of protons 19, number of neutrons 20, right? And calcium 2040 has number of electrons 20, number of protons 20, number of neutrons also 20. So again see, they both have same number of neutrons. So therefore they are examples of isotones. Okay. So this is another example of isotone. Okay. Atoms having same number of neutrons are called isotones. So here same atomic mass is 131, number of neutrons 53, number of electrons or protons is 78 in this. Okay. So number of neutrons, here also it is 53, here also it is 53. So these two will be isotones. Okay. So I hope it is clear. Okay. Now we will define what is radioactivity. Okay. Now this phenomenon of radioactivity was discovered in the year 1896. Okay. Now, once in a dark room, this scientist called Henry Becquerel, you need not remember the name of the scientist, nobody will ask you, I am just informing you. He was sitting in a dark room, and he was in a dark room and he left uranium salt placed on a photographic plate wrapped in a black paper, and he left it in a dark room and went away. After some days, he was surprised to find that the photographic plate was affected. Later on, the same observation was made with other salts of uranium. From these observations, this scientist Henry Becquerel concluded that uranium and its salts by themselves emit some kind of radiations which can pass through the cover, that is, they were wrapped in glass paper, sometimes they were wrapped in wooden, they were kept in wooden box, glass box, etc. of the photographic plate and affect it. They can pass through these things and they can affect the photographic plate. Okay. So these radiations were called in the beginning Becquerel rays. On further investigations, these radiations were found to be of three types: positively charged, negatively charged, and uncharged, which were then named as alpha, beta, and gamma radiations. And the substances which emit these radiations are called radioactive substances. So, substances which emit and which disintegrate, they keep on emitting these radiations and they keep on decaying or they keep on disintegrating. They keep on reducing in their quantity by the spontaneous emission of radiations. They spontaneously emit radiations. Okay. And these substances are called radioactive substances. Example are uranium, radium, polonium, thorium, actinium, etc. So, the isotopes of nearly elements of atomic number which are higher than 82. I was telling you the heavy atoms, heavy atoms of elements, they exhibit this property. They keep on emitting radiations. Okay. That is, after lead in the periodic table, these heavier elements are all radioactive because in their nucleus the number of neutrons is much more than the number of protons. That is why these are heavy atoms. So, such elements are called natural radioactive substances. Okay. So, now this radioactivity is a nuclear phenomenon. It is happening from the nucleus of the atom actually. Okay. So, first of all, what are radioactive elements? Substances which disintegrate or decay by the spontaneous emission of radiation. So, when these atoms keep on emitting radiations, they keep on reducing in their quantity. They keep on disintegrating or they keep on decaying. And such elements are called radioactive elements or radioactive substances. Okay. Now, the examples are uranium, radium, polonium, thorium, actinium, etc. And this phenomenon of radioactivity, this is a nuclear phenomenon. What is this radioactivity? It is the phenomenon or process of spontaneous emission of alpha, beta or gamma radiations from the nucleus of the atom during their decay. So, what are radioactive substances? Radioactive substances are those substances whose atoms spontaneously emit alpha, beta, gamma radiations. They are called radioactive elements or substances. Now, radioactivity is a phenomenon or the process of spontaneous emission of alpha, beta, gamma radiations from the nucleus of atoms during their decay. That process or that phenomenon is called radioactivity. Okay. So, let us first define radioactive elements. Okay. Radioactive elements. Now, what are these? Substances. The substances whose atoms emit radiations, called alpha, beta and gamma, alpha, beta and gamma radiations. Okay. Substances whose atoms emit radiations and disintegrate or another word for disintegrate is decay by the emission of these radiations, by the emission of radiations are called radioactive substances. The substances whose atoms emit radiations. What are the radiations called? Alpha, beta, gamma. Alpha, beta, gamma radiations, and disintegrate or decay by the emission of these radiations. Such substances are called radioactive substances. Now, examples of radioactive substances are uranium, radium, polonium, thorium, actinium, etc. So these are an example. These are all examples of radioactive elements. Actually, the isotopes of all elements whose atomic numbers are higher than 82 are all radioactive. Why? Because in their nucleus, the number of neutrons is much more than the number of protons. So, such substances are all called natural radioactive substances. So, that means the atoms of radioactive substances have more number of neutrons in their nucleus than the number of protons. Okay, so atoms of radioactive substances have more number of neutrons than the number of protons in the nucleus. Okay, now this process of emission of radiations, which radiations? Alpha, beta, gamma, from the nucleus of atoms of heavier elements is called radioactivity. So radioactivity basically happens by the nucleus. The electrons are not responsible for the phenomenon or process of radioactivity. The neutrons are the responsible agents. So radioactivity is basically a nuclear phenomenon. Okay, so radioactivity is a nuclear phenomenon. It is the process of spontaneous emission of alpha or beta or gamma radiations from the nucleus of atoms during their decay. So this process is called radioactivity. So let us now define radioactivity. So radioactivity is first of all a nuclear phenomenon. Okay. Radioactivity is a nuclear phenomenon. It is the process of spontaneous means on its own it happens, spontaneous emission of alpha or beta or gamma radiations from the nucleus of atoms during their decay. Is it clear? First of all, radioactivity is a nuclear phenomenon. Why? Because the nucleus or the neutrons in the nucleus are responsible for this phenomenon. And it is the process of spontaneous emission of alpha, beta or gamma radiations from the nucleus of atom during their decay. Okay. So from a radioactive substance containing a very large number of atoms, there is no way to know when or which nucleus of the atom will decay at any particular moment. Hence, the radioactive decay is a random phenomenon. That is, there is no law by which the disintegration of individual nucleus can be predicted. Which atom will emit the next radiation is not sure. Which nucleus will first emit and which will emit second and which will emit third, such a law is not there. It is a random phenomenon. Okay? Now I have been discussing about all along the definition alpha, beta, gamma radiations. Now we will learn in detail about these radiations, alpha, beta, gamma radiations. Okay? So we will learn in detail about emission of alpha, the symbol is this, beta, the symbol is this, and gamma, the symbol is this, radiations. Okay? Now we will learn in detail of these things. Now, in 1903, in the year 1903, Rutherford experimentally studied the nature of radiations emitted by these radioactive substances. He found that on subjecting these radiations, which radiations? Alpha, beta, and gamma radiations. So he found that on subjecting the radiations given out by the radioactive substance to a magnetic field, what he did? He allowed these radiations to pass through a magnetic field in a direction perpendicular to their path. Which one? The magnetic field was applied in a direction perpendicular to their path. Means if this is the direction of the radiations, if this is the path of the radiation, then the magnetic field was applied perpendicular to the direction of the radiations. Then they separate out into three distinct constituents. Okay, they separate out into three distinct constituents, these radiations. Okay, when they are applied, or when a magnetic field is applied perpendicular to the direction of the radiations. So these are the radiations coming, alpha, beta, gamma radiations. So a magnetic field is applied perpendicular to the direction of the motion of the radiations. So then they found that these radiations separated into three types of radiations. Okay. So he found that on subjecting radiations given out by radioactive substance to a magnetic field in direction perpendicular to their path, they separate out into three distinct constituents. Now, some of them turn to the left, some of them turn to the right, and some go undeviated. Okay. So those which turn to the left must be positively charged and are called alpha particles. Okay. So those which turn to the left. Now this diagram is illustrated in this manner. I will show you. See, this is the radioactive sample. Okay. Now from this sample these radiations are coming out, and then this is the magnetic field applied perpendicular to the direction of the radiations. Okay. So now he found that these radiations, when applied by a magnetic field in a direction perpendicular to the direction of motion, they got deflected in three directions. So the one which deflected towards the right or towards the left, sorry, this left, let me discuss first. Towards the left, they are alpha particles. Towards the right, they are beta particles or beta radiations, alpha radiations, and the one which went straight undeviated are the gamma radiations. So, those which turn to the left are alpha, those which turn to the right are beta, and those which go undeviated straight are the gamma radiations. Okay. So these radiations contain particles. Alpha radiations contain alpha particles, beta radiations contain beta particles, and gamma radiations contain gamma particles or gamma radiations. Okay. Now, those which turn to the left, Rutherford decided, must be positively charged, and those which turn to the right must be negatively charged, and those which go undeviated must be uncharged or neutral and are called gamma radiations. Okay. So these gamma radiations are electromagnetic waves similar to light waves and are therefore not affected. Light waves are also not affected by the magnetic field. So the gamma radiations are electromagnetic radiations or electromagnetic waves which are not reflected by the magnetic field. Okay. Now, this is the effect of magnetic field. Effect of magnetic field. Now, similarly, the radiations given out by the radioactive substance are subjected to an electric field again in a direction perpendicular to their path. They again separate out in three constituent directions, three constituent paths or three constituent particles as shown in this figure. So, this positive and negative indicate that this is an electric field with positive and negative charge. So, those which turn towards the positive plate are negatively charged. So, this is the positive plate. So, those radiations which turn towards the positive plate must be negatively charged because opposite charges attract. So, they are the beta radiations or beta particles. Those which turn towards the negative plate must be positively charged. So, they are the alpha particles. Okay. And those who go undeviated are the gamma radiations. Okay. So, these are the three types of radiations. Okay. Now, we will learn the properties of the constituent particles of these radiations, that is properties of alpha particles, beta particles and gamma radiations. Okay. Is that clear? Or let me stop here. Now the properties of alpha particles, gamma particles I will continue in the next class. You go through this, whatever I have taught till now. Read them, go through it, read your textbook, read your notes. If you have any doubts, you can ask me in the next class. And in the next class, I will start with properties of alpha particles, beta particles, properties of gamma radiations, and then some more things. Okay. So thank you children for watching. Let me stop here. Take care. God bless you.